Welcome friends, Igor is here, and in this video we will learn what linear systems are easy to solve by using the reduced row echelon form matrices. In this lesson we will define the reduced row echelon form of a matrix, we will define elementary row operations, which are going to be the analogs of equation operations we perform on a linear system, and we improve the efficiency of our strategy for solving linear systems because we will be using row operations on the augmented matrices rather than the equation operations on the equations of the linear system. We already started implementing our strategy for solving linear systems by discovering what we can do to a linear system to preserve the solution set. We proved that we can use equation operations to transform a given difficult linear system to an easy linear system, which is supposedly easy to solve. We need to have a very clear goal in mind. When we transform the linear system, what is that simple form that we're looking for? And we will describe these easy linear systems by using matrices. A matrix is in reduced row echelon form if it satisfies the following four conditions. All zero rows are at the bottom of the matrix. The leftmost non-zero entry of a row is equal to 1, and it is called a leading one. Each leading one is the only non-zero entry in its column. The leading one in any row is farther to the right than the leading ones in the rows above. Let's set some additional terminology that we will be using throughout the rest of the course. Suppose that we have a matrix in reduced row echelon form, then the number of non-zero rows of that matrix will be denoted by R. A column of the matrix which contains a leading one will be called a pivot column. Keep in mind that these notions make sense only for the matrix in reduced row echelon form. Also observe that each non-zero row corresponds to exactly one leading one. Also, each pivot column corresponds to exactly one leading one. Therefore, the number R, which we initially defined as the number of non-zero rows in the reduced row echelon form matrix, is also equal to the number of leading ones, and it is also equal to the number of pivot columns. Later in the course, we will call this number the rank of the matrix, and this is why we denote this number by letter R. Here is an example of a matrix in reduced row echelon form. It has two zero rows, which are located at the bottom of the matrix. There are three leading ones. Each of the three non-zero rows has a corresponding leading one. R is equal to 3 because there are three non-zero rows. We also have three pivot columns. These are columns 1, 5, and 6. All other columns of this matrix are the non-pivot columns. Here is an example of a matrix which is not in reduced row echelon form. There are many problems with this matrix. First of all, we have one zero row which is not at the bottom of the matrix because it is located above two non-zero rows. In row number 2, the leftmost non-zero entry is equal to 5 rather than 1. Also, the column number 7 contains a leading one, so it is a pivot column. Yet, the leading one is not the only non-zero entry in this column because the first entry in this column is equal to 7. Now that we can represent linear systems effectively using matrices, we will find the analogs of equation operations in terms of matrices. These are called row operations. There are three types of row operations, and they are derived from the corresponding equation operations. Operation swap allows you to swap the location of two rows of a matrix. In a scale operation, you multiply every entry in one given row by the same non-zero quantity. In a replacement operation, you multiply each entry of a given row by some quantity and add the result to the corresponding entries in another row. By corresponding entries, I mean entries which are located in the same column. Here is an example which illustrates that performing equation operations on a linear system is equivalent to performing row operations on the augmented matrix of that linear system. First, let's perform an equation operation on a linear system. We are going to multiply equation number 1 by -2 and add it to equation number 2. Now, let's perform the same replacement operation, but now using row operations. For this, we take row number 1 of the augmented matrix, multiply each entry in that row by -2, and add the result to the corresponding entries in row number 2. If you look at the transformed system and the transformed augmented matrix, you will recognize that this is the augmented matrix of that linear system. To help us keep track of what operations we perform to transform the linear system, we will set the following shorthand notation for the three types of row operations. We are going to say that two matrices are row equivalent if one can be obtained from another by a sequence of row operations. Each of the three row operations is reversible. Please think why. And therefore, if a matrix A can be obtained from a matrix B by a sequence of row operations, we can also obtain a matrix B from a matrix A simply by reversing that sequence of row operations. Here is an example of two row equivalent matrices A and B. To show that they are row equivalent, I just need to construct a sequence of row operations which transforms matrix A into the matrix B. Let's start with the matrix A, and the first operation is we are going to swap the location of rows number 1 and number 3. Then we are going to use a replacement operation. We are going to multiply row 1 by -2 and add the result to row 2. And now you see that it takes only two row operations to transform the matrix A to the matrix B. The next theorem explains why we introduced the notion of row equivalent matrices. Our main motivation at this point is to solve linear systems. And if two linear systems have row equivalent augmented matrices, then the linear systems are actually equivalent. To prove this result, let's recall what we just discovered. Performing row operations on the augmented matrix is equivalent to performing equation operations on the corresponding linear system. We already proved that equation operations preserve solution sets of linear systems, and therefore performing row operations on augmented matrices results in augmented matrices which represent equivalent linear systems. And now, to solve any linear system, instead of performing equation operations which require writing out complete linear systems, we can simply perform row operations on the augmented matrices of these systems. And this saves us a lot of time because we do not have to write every time all the extra symbols. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will learn how to use the Gauss-Jordan elimination algorithm to solve any linear system. I will see you later.